All right, let's get started. So I just had this idea because somebody asked me some interesting question. Yep. So I'm reminded I should make an advertisement. I haven't made any real advertisements yet so far, so I can make one advertisement. This is not all LEGO. So there's this LISA project, a space mission, which is scheduled to fly in the early 2030s, which I'll probably be going like this at the time. But you have the future, and now. So LISA is going through a phase of basically getting organized, forming groups and things like that. And so if your group has an interest to join, now is a really good time to join. And the threshold is actually very low. You can become a full member, an associate member. If you're an associate member, you have basically no obligations, but you can participate in the science discussion. So it's if you think that your group at home might contribute something or be interested, talk to your advisor, advertise it. You go to the LISA website somewhere. Yeah. You mean what are good recipes to yeah. I haven't. Yeah. So in fact, okay. Well, so I'll make my advertisement. This is my advertisement, and then also I had a question for you, basically to do some thinking during the lecture, which is what you want to hear tomorrow. Okay. I think let's see if I finish the theoretical material that I have today, but I'm very flexible about what exactly we do tomorrow. I can do a number of things, but I think what makes most sense is what's most useful to do. So, for example, just having a little bit of discussion of what Rodrigo just said, maybe that's a useful thing to just spend 15 minutes or so, maybe with all the lectures together, or I don't know. Just think about what would be really useful for you to discuss, to ask, or further things to learn about, things theoretically that it would be nice to know, or maybe talk a bit more about practical things. So if you have some desires, what would be nice to what you haven't not yet learned, and maybe Friday my lecture would be a good moment for that. Just let me know afterwards in the break or after this lecture, and I'm extremely happy to follow your suggestions. Anyway, so I wanted to. So this is this lisamission.org website. That is register as a scientist. Click, and then comes a form. And so it might be that something that you want to advertise to your advisor, and certainly if your advisor may know other people that can explain a little bit more what's behind this, what the opportunities. But I'm certainly also very helpful if somebody sends me an email to explain to people what's the current status of this collaboration and how it's organized and where it's going and so on. Okay. So this was the advertisement. Now, let's. So I have too many different. We start with this. All right. So now I'm falling behind, and so this is. I'm now a full lecture behind, but this is going to be a very short one, and I might discover there's lots of overlap with the previous hour. So maybe we can. It's just if Jan just talked about it, maybe just let me know and we can skip some material. I guess we have to switch off the lights now. No? Which one is it, Frente? Is this better? So I wanted to say a few things about gravitational wave signals. So now let's see if this movie plays. It has music also. So these are all the like regular detections so far. The dynamics, but it's not just that. All right, it's a short movie. Okay, not just the dynamics, but of course what we actually observe is the gravitational wave signal. So how, if you have some numerical space-time, how do we get the gravitational waves out? I thought I flashed this. This is a very old slide, but when we did the student talks, diagram and the Penrose diagrams were featured quite prominently also in the student talks, in a very nice student talk yesterday. So I'll say something about this, a bit more about it. So isolated systems as models of sources of gravitational waves. This is something to understand. So if you think of some astrophysical processes, so here astrophysical is meant as opposed to cosmological, okay, somehow involving the entire universe. So astrophysical is, I don't know, a supernova, the collision of two black holes, these kinds of things, all right? So what you would expect is essentially independence of the large-scale structure of the universe, all right? That for studying this black hole merger, which takes 1 second, probably the local value of the cosmological constant will not be very important. This doesn't mean that this event cannot tell you anything about cosmology, because it's very, very. Waves have traveled a long time. You might use this to measure. There are other things which tell you something about cosmology, but for the local dynamics and how this local system waves, you should be able to just treat it as a related system. Okay, hopefully, still, not. Consider other things. And then radiation is going to leave this system. So that the idea is that the physical kind of idealization is this, as you call it, an isolated system. And so the idea is that basically at very large distances, the geometry becomes flat or approaches some cosmological background geometry. But essentially it becomes flat, locally flat. And then if you go even further away, then you will start to see the cosmological effects. But for this you have to go to very large distances. And then general relativity, all the most favorite quantities of a physicist, what favorite quantities, mass, momentum, emitted gravitational energy, they can't be defined unambiguously in some local or quasi-local way. Okay? So very difficult to have a definition in some finite neighborhood of how much energy there is. Okay, so in general relativity, it's not possible a rigorous definition of saying how much energy is in the or you can have many rigorous definitions, but it will be different. Okay, so there's no unambiguous one. What you can do is basically when you go very, very far away. So we had these Penrose diagrams yesterday. If you go to infinity, in particular null infinity, then you can say what's the gravitational waves that leave the system through null infinity. Oh, note again that there's time different. For example, you can expect that if you go very far away from your space-like direction, it will become flat. If you go in a null direction, you follow a light ray, also you go far away from the source, it will become flat. If I go infinitely far in a time-like direction, I cannot expect that it's flat. So if I just stay on the Earth and I wait a very, very long time, 1 billion years, the gravitational field will not have changed much. There's still the gravitational field of the Earth. It's not getting flat. Okay? So it's going to be flat in this direction and this direction, but not in the time-like direction, unless it's really Minkowski's, and there are no sources. What else did I want to say? I wanted to say something else, which I forgot. Yeah, maybe one physics comment is that the basic reason why you can't do this is fundamental in general relativity is because the equivalence principle. Because in the equivalence principle, you can transform away the gravitational field. You can somewhat locally pretend, no, this is not gravitational field, this is just your frame of reference. And so therefore, it's not it's ambiguous what is the local energy density. And if you want to combine, if you want to find the total energy density is the energy density of the matter plus the gravitational energy density, which you can't define, so you can't define it in total. Okay, so you have to go infinitely far away to compute, for example, how much gravitational waves are leaving the system. So this is a major complication. So really, radiation lives at infinity, and if you think of having a telescope or LIGO or whatever, which views some astrophysical process here, so I don't know, some collapse of some matter, you look at this with your telescope observatory along ingoing null rays like this, and so your instrument is up here, and you just look inward into the space-time, and effectively you are at astronomical distance. All right? So go now? All right. So effectively you are living here, you're at null infinity. All right? That's where your observer is. Now, in practice, what we do, so there's a lot of work which is going on to make this all rigorous and calculate your gravitational wave signal at null infinity. In many practical applications, this is very difficult. I would just do it at a large separation, or you do it at several separations from the source. A large one, and even larger one. You have basically convergence, like the numerical convergence that we discussed in the grid resolution, but now you have convergence in how far you're away from the source. It has its technical problems. More or less, this works quite well. And if you want to use, for example, numerical waveforms for some type of gravitational wave data analysis, usually you have this kind of waveforms which in some way they have been extrapolated to infinity. Which comes with some numerical artifacts, usually smaller than other artifacts that you have. All right. And so now how do you compute the gravitational wave signal is inherent in some space-time. We have done your simulation, how you compute the gravitational wave signal. There are different methods. The one that is most easy to code in a numerical code, and so the one that is basically provided by all of the codes that study collision of black holes or neutron stars or similar things, is they compute an object which we'll get to here, which is called psi, and it's a particular projection of the Riemann tensor. Okay, and so this is related. I'm not sure. I don't have this. Do I have the formula here? No. No, here it is. Sorry, here it is. So the usual gravitational wave signal that you can consider is the strain. This is the kind of quantity which is measured by LIGO, for example, the metric perturbation, the change in arm length of the detector divided by the length of the arm. Is this quantity? As you see here, so where everything is rigorously defined, this is just 2 time integrals of this particular component of the Riemann tensor. Okay? In fact, some people define with a minus, so there's lots of conventions that can create a huge amount of confusion, a huge amount of emails, and of course here just to confuse people, but up to minus signs, this is your strain, and this is how this is related to a particular component of the Riemann tensor. These things which make the contraction, this is what is referred to. So there's basically your unit time-like vector that plays a role in this, and your unit spatial vector that points outward from the source. And then these two are essentially your angular directions, but for reasons of wonderful elegance, complex object. You see this, there's some object M, and another one is the conjugate bar, because it has very nice mathematical properties. Essentially, the angular directions, and they form a particular of psi4. If you have general relativity, then so psi4 is a complex number, so it has 2 degrees of freedom, because, so this is your talk yesterday, the complex quantities, they allow you to encode the freedom, the plus polarization and the cross polarization of the gravitational wave signal. So a single complex number has all the information, and so this is how your polarizations are defined, but then this psi4, also the H, they have all the information included in a single complex number. And there's a lot of very deep and interesting maths where these kind of objects which encode the information as a complex number, you call them spin-weighted fields, and in particular the ones that we are interested in, they're called spin weight 2 or minus 2, depends on your conventions. So spin weight 2 fields. There's some natural of the choice for these tetrads, but basically you have a lot of freedom, because inside in the space-time where you have curvature, there's no real for a curve black hole you can make some very nice and elegant definitions, but if you have a general gravitational waves sloshing around and some matter, then there's no unique definition of this. Okay. What else? And then I'm sure you talked about spherical harmonics. No. Right. So this is the wave signal as a function of time at theta and phi. The angle, celestial sphere. Okay, the sky. But it's very useful. So usually what happens is that the angular variation of these waves is not very large. And so if you make a decomposition into spherical harmonics, then you usually just need a few of these spherical harmonics. Okay? This spherical harmonic decomposition, it converges very quickly. And so usually you take a few of the spherical harmonics to represent your signal. So you basically, what you take with your signal, you project it onto these appropriately chosen spin-weighted spherical harmonics. So you might know other types of spherical harmonics if you study a scalar quantity, or if you study the electromagnetic field, where you do a similar decomposition, and that's electromagnetic is a vector. And so here, these fields are really tensors, and so they also these things are also referred to as tensor spherical harmonics, because the perturbation is encoded in this. It's a tensor. So these are if you look at you Google spherical harmonics, these formulas may look a little bit different, because these are not scalar spherical harmonics, but tensor or spin weight 2 or minus 2 spherical harmonics. And so what you do is you basically take your signal and you this one is the LM harmonic, and so you describe your gravitational wave signal in terms of these coefficients. If you see a plot of some gravitational wave signal, in so for example, what I can draw very well. It's so this is what the kind of thing that Jan also has done. So here's your gravitational wave signal. So this may be one of two things. You have to always check which one it. It could be so this is a real function, obviously. So this is the real part of something. It could either be the real part of the strain as measured by the detector. So this is essentially the projection of the gravitational wave signal onto your real function. Is how the arm stretch. Okay. Or it could simply be the real part of this coefficient. They will look very similar, but it's a very different quantity. Okay, so if you look at some observational paper and there's some waveform, it's gonna be it's not gonna be this. This is what has actually been measured. But if you look at some theoretical paper of modeling these waveforms, understanding these waveforms, it's probably simply this quantity. Okay, and they will be related by some factors and some maths. All right. And now if you compute some physically interesting things from this, then it turns out, because they are orthogonal, often you have very simple formulas. So for example, the radiated energy, dE by dt, what is this now? This is some integral where these coefficients appear, but because they are orthogonal, this is simply a product of the squares of all these coefficients, which is a very simple formula. You don't have to cross multiply them all, but this is simply a sum of all the squares. You have to, so this will depend on the distance from the source, and then you have to take the limit of the distance of the source goes to infinity. But usually you can't really do that, so you do some kind of convergence analysis, very similar to what you do for numerical convergence. Because these modes, they are oscillatory complex functions, which are hard to understand. Very often you write these complex functions as some amplitude times e to the I some phase, and then you deal with the amplitude and phase, which are real functions, which are much easier to understand. Then you compute your frequency. Divide by dt. This is a bit of a slip here. When you compute frequency, you will call this the frequency. You have to be very careful, of course, because you can talk about the frequency f, or the angular frequency, which has another 2 pi, which are another source of endless confusion. Just to point that out. When people make models of things, usually it's easier to have this one, and this avoids factors of pi. But as soon as you compare things with the actual data, then you use the f frequency in hertz, and not this thing in radians per second. So you have to be, at some point there's a change of philosophy, but the theory will like this. When you compare to the experiment, f. Okay, and then these are more of these types of formulas that one has to have seen. So, for example, the e by dt, the components of the radiated linear momentum, components of the radiated momentum. Here I was lazy, I just wrote the z component. You have a very similar form. There is some integral of the SAIFR quantity over time. You don't have to make a picture, I can give you the references. This is the easiest one, but you see that here you multiply this with a certain unit vector to get this direction, and for the angular momentum also you have some derivatives, but the basic structure is very, very similar. So these are the kinds of, so you take some sphere, for example, that is far outside, and you compute these quantities for whatever you need, and then you have to check whether if you go to a larger sphere, you still get the same result. All right, there are similar surface integrals, not for the radiated which are defined at a certain radius, let's say some very, very big sphere. They don't have ambiguous physical meaning. If you really want to get something physics, then you always have to operation goes to infinity. Okay, you can, if you want to be really fancy and and posh, and you show off that you're really smarter than other people. Whenever there is a conversation about these quantities, they will call them the ADM energy, ADM linear momentum, and ADM angular momentum, and they look very, very similar. They look similar. Okay, then they will be very impressed. All right. Also, you should be aware so you can give these quantities two different names. You can call them ADM for Arnold Desarmisna, people that have studied the Hamiltonian evolution equations for GR, and so all these energy, momentum, they arise in the Hamiltonian description of GR, and they basically correspond to G at spatial infinity. All right, but what we have said is that, well, it makes a little Penrose diagram again. Here's our Penrose diagram, or maybe for one black hole. So up there we have a singularity, maybe. Here's spatial infinity. So if you compute your energy at spatial infinity, here it's called the ADM mass, or ADM energy, depending on exactly what quantity you consider. But if you compute it here, then it has a different name. Then it's the Bondi quantities, or Bondi energy. Okay. So this one is because it's at infinity, and things take an infinite amount to reach infinity. This thing is constant in time. This doesn't change, but this does change. Obviously, what happens is that this one decreases with time, which is hard to prove. But the thing that happens in GR is that that this quantity decreases with time, because you radiate positive energy out of the system, and so this Bondi energy decreases with time, which is essentially just the same quantities, but not evaluated as you go here, but evaluated in this direction. All right. In fact, it's going to be probably probably going to be to have some mathematical relativists make a concrete statement that this is really just the same quantities going to null infinity. So I only say this here because I'm on record. But this is the case. This is the same objects going to null infinity. All right. Oops. What we have here. Then so we had recoil yesterday. So I just wanted to mention recoil again, obviously with the same one. So if you have unequal black holes, like here, they're not the same, they have different masses or different spins, then the gravitational waves are emitted asymmetrically, so more in this direction, for example, than in this direction. So this is like if you have a lawn sprinkler that's a bit asymmetric, it's a bit broken, more water comes out here than there, and so the whole thing is going to move across the lawn. Okay? If you don't have radiation reaction, if you don't emit gravitational waves, and then you emit more in this direction than in this direction, well, half an orbit later, it goes the other way and it cancels out. Okay? But if this exactly, and slowly, this effect will increase. In fact, it increases only very, very slowly, and almost all of the effect comes right at the end when the two things merge together. It was a big question how large this effect is, because so the escape velocity of the largest known galaxies is on the order of 2,500 kilometers per second. And if the final black hole moves faster than this, it can just leave the galaxy. If you have a smaller cluster, globular cluster, something like this, of course, the escape velocity is much smaller. And so these first calculations were performed in 2007, end of 2006, 2007. And so it turned out, if you don't have spin, the max recoil happens for about a mass ratio of 3. It's about 170 kilometers per second. But if you have spins, then you can have much larger recoils. And they can indeed be a few thousand kilometers per second. Let's see how we compute this. In fact, here, oops, hello. Here I have these formulas. They look a bit complicated. So this is so the recoil. Momentum. So you see these ugly formulas. Again, you have to take a limit. But in fact, these formulas are now written in terms of the modes. Now what before was, so we have these different modes. Here, these A's and B's, they're just numbers. We're not interested in these numbers. Here we see so HLM is the LM mode of the strain, LM plus 1, and so on. See that all these terms, for in X and T, for example, you have different L's and M's. So the recoil is generated by the interaction of one mode with some other mode. Okay? Well, it's one, essentially. And then there is some. Now, so just knowing this, what do you expect? Let's maybe slightly rephrase. So if you have no spins, okay, what would happen? In which direction can the recoil go if you have no spins? If you don't have spins, you can't have precession, and so the orbital plane is preserved. Perfect symmetry. So like your northern hemisphere and the southern hemisphere, they are the same. Okay, and you have equatorial. The orbital plane is preserved. Have this kind of recoil, in which directions could it go? Any ideas? So it has to be in the orbital plane. by symmetry, because nothing can, because if it go off the orbital plane, so here we have our orbital plane, right here our spins are sticking out like that, maybe one goes up, one goes, the things are orbiting around each other, but the northern hemisphere and southern hemisphere of this system, of the universe, they're exactly identical. The energy goes this way as it goes this way. And so there can't be any imbalance of more energy goes this way, more energy goes that way. So the recoil has to be somewhere in this plane. Okay? But if you do have, and so if you add spins, but the spins are non-precessing, it's the same story. The recoil has to be in this plane. But if you have precession, if your spins are more general, whatever, like this, and like that, then you also can have a component. So then, maybe more energy goes to the north than to the south. Okay? Now, in this case, what can happen, is that what are the dominant spherical harmonics? Well, the quadrupole. So the dominant ones are H, LM. So sorry, H22, and then the one there's always a plus M and a minus M, and the H2 minus 2. One of them basically lives mostly in the northern hemisphere, and one of them mostly in the southern hemisphere. These are by far the strongest modes, by far. Everything else is subdominant. So the strongest recoil you can get when you have interactions between these two. For recoil, you always need some mode mixing, interaction between different modes. The strongest effect you can get is when you have an imbalance in these two, and more energy goes in this one than goes in this one, for example. In which direction does the effect go? Well, because the imbalance is between north and south, then this effect goes, either north or either south. And this is the effect that you can get really, really large recoils of thousands of kilometers of second. Second is the imbalance between these two. And basically the resulting binary, so they orbit around together, and suddenly the whole thing shoots up with 2,000 kilometers per second. Okay? All right. Now, oops. I thought a movie comes. Where's the movie? Apparently no movie. Okay, it's anyway. Movie by Carlos, the key person in Argentinian radio astronomy now, and it worked on the laptop. It's a very nice. We can look at it. You can find it on the website. It's a quite nice movie that shows the asymmetry of the gravitational waves. So when they're far apart, you see this kind of quadrupole structure, but as they come together, the quadrupole gets deformed a lot, and you see that the gravitational wave emission becomes very asymmetric. So you have a lot of recoil, and it just shoots off in one direction. Okay, so just 2 minutes, and so now let's start the next lecture. All right, so now we'll talk more about black holes, and so there's going to be a little bit about some history, and then I'll mostly talk about gauges and evolution systems and strategies how to avoid the singularity, which is really just these two topics are very tightly coupled together. All right. Now, so before we do this, let's think about how difficult is the whole thing really with numerical relativity. How difficult is it to evolve the numerically evolved system in full? I've seen this list somewhere in a paper by Franz Pretorius, I think. And so this is my version, kind of similar, my version of this list. And so a good way of classifying these things is basically where the mass energy comes from. Okay? If the mass energy in the system, it comes from the object's rest mass, that's the easiest case. Okay? So this is the astrophysical case. So basically, your black holes or neutron star or whatever it is, they move much slower than the speed of light. And so the dominant energy comes from their rest mass. Okay, not from. In fact, right before the merger, this is not completely true anymore, but mostly this is perfectly true. No, Now what's the... I cannot read my own slide. It doesn't make any sense. Is the object's rest mass? Is the rest mass of the object? That's an interesting... that's interesting. So whatever mistake this is. So if you have highly relativistic... Well, this is a very old slide. I've shown this like at least 4 times already. If you have very relativistic collisions, then you have a significant contribution from the kinetic energy of these objects, and the kinetic energy can be comparable with the rest mass, and then things are significantly more complicated. An even more complicated case is when the mass energy is actually dominated by the gravitational waves. When you emit so much gravitational waves that they have more energy than your matter, your particles. The extreme case would be gravitational waves, that the gravitational waves themselves collapse black hole. That we don't expect this to happen in astrophysically, but to understand general relativity, this is a very interesting problem that has drawn a lot of work. So in this sense, basically, the binary black hole problem. Yep. I would say none. I mean, you could maybe in the like very early universe, maybe you could imagine such a situation, but I think it would be hard. It's a very interesting question to understand the structure of general relativity, but the astrophysical interpretation is probably not very important. But maybe it would be if someone finds an application, but I'm not aware of any. So in this sense, basically the binary black hole problem took us years to figure out. That's really the easiest case, and then other things become more difficult. Of course, then you have limiting situations. For example, extreme mass ratio in spiral, where other parameters become extreme or very close to the extreme Kerr solution, really ultra-relativistic black holes, or critical collapse that I'm going to say something about. If you have some kind of threshold behavior where depending on some parameter, either this thing happens or this thing happens, but then for a pixel value, something just in the middle, for this kind of fine-tuned or then of course things become much more difficult. The easiest case is of course then once you go down in symmetry, so for example just having spherical symmetry, lots of interesting things in spherical symmetry. What you don't have in spherical symmetry is gravitational waves. So if you want to have like waves phenomena in spherical symmetry, you have to put some, so for example you can use a scalar field to kind of mimic some of the behavior of gravitational waves, but not all of it, in spherical symmetry. You can do non-trivial topology, for example, which can be interesting for modeling the entire universe, for modeling cosmology. And then things make a big step up in complexity if you add matter fields, which is what Louis is going to talk to you about next week. All right, so this is a little bit of a classification of what different problems arise and what is their difficulty. Now, I wanted to mention this story, which is now quite old. This was a really big success story of numerical relativity, which goes under the name of critical collapse. And so I don't really have references. Here we have. So this happened in about 1990. So this is a long time ago. And it was the first big contribution of numerical relativity to discover something new in general relativity was that had somehow escaped people until then. All right. The question is what are the possible final states of a gravitating system? So if you think of a big lump of matter, then what's going to happen is also maybe some wavy matter, some waves. If the field strength is kind of, they may interact, but eventually disperse again, and all the waves and they interact non-linearly, they an apparent horizon, a trapped surface, and they will form a black hole. The question is, if you have some one parameter family of initial data, so this is my big space of initial data, and so I have some curve in this space, and so here in this part they form black holes, and in this part they disperse to Minkowski. What happens in the middle? Okay. For another question is, if you think of the biggest solutions, maybe they form very big black holes. That maybe going this way, you form lighter black holes. Can you form a black hole which basically just zero mass? Can you make arbitrarily small black holes? And if you make them really, really small, singularity. Okay, can you do that? Can you fine-tune? So this is not really an astrophysical question. It's some fine-tuning, but it's very interesting for general relativity. Can you fine-tune your data to, like you can? The early 90s by Chopdwick, you can do bisection. You say, okay, let's make this curve, the amplitude could be you vary the amplitude of the wave or the width, pulse or something similar. So you say, if I make my amplitude small, it disperses to infinity. If I make it very large, it's a black hole. So then we use standard bisection to move around in the parameter space, closer and closer. And then something very interesting happens. You discover some universal behavior, so that if you make another curve here, entirely different type of curve with a different parameter, you find that the limiting solution is universal. It has universal properties. It has more symmetries than the general solution, and has a number of interesting properties, like some scaling behavior with a universal exponent, which reminds you of phase transitions in statistical physics, for example. This was first found in spherical symmetry for a scalar field, but since then has been found for all kinds of systems at some critical point between basically dispersing, between forming a black hole. So this is a very interesting and big topic in numerical relativity, which is not directly related to gravitational waves and astrophysics, but it's good to be aware of. Yeah, this solution. This kind of solution is called self-similar. So you see these echoes, and with each echo, you repeat the echo, but smaller and with shorter time. Okay. So in a space-time diagram, this would be a self-similar solution. I just want to flash this, just to be aware. There are other interesting things you can do in numerical relativity, which are not directly related to astrophysics. This is an overview slide of the long history. Again, I don't want to really go into that. You just see at the beginnings in the 60s with this 3+1 formulation, the work of ADM, the first ever attempt to compute the collision of two black holes in 1964, and then a lot of theoretical development. For example, the Bowen-York initial data that I talked about yesterday. This was in the 90s, or this principle of using excision to evolve black holes. So you see a very long history. You see a big increase in the performance of computers, and some other milestones. There was a big project in the US which was supposed to lead to successful evolutions, which it didn't, because people discovered all these instabilities that I talked about before. But you see how, for example, how this goes together with funding LIGO, starting the construction of. So there's a long history before this, but then once they had to wait for a long time until 2005 with these breakthroughs of actually being able to first do maybe just half an orbit and eventually more. All right. What do I really want to say here? Let's see. Another. So one thing that I find kind of interesting is so 2005 when this big breakthrough happened. So this is this 2005 simulation. This was the fourth science run. So LIGO had done a first, second, third, fourth science run. So there was already a large state of maturity for the LIGO detectors, and we didn't have any waveforms really that described the merger of two black holes, which was a funny situation. Only in 2002 was the first numerical simulation of what's the energy loss in a non-spinning equal mass merger, which gave a result of about 3%, which is this calculation. So really just making an ultra short simulation of just the merger and computing for the first time roughly how energy is actually released. Was it going to be 0.1% or 20%? It was not really known. So this was done really quite late. After this initial breakthrough, there was very rapid development. There was about 10 groups or so that could do this simulation for about 2 or 3 years. There was very rapid development. Every 2 weeks there was a new phase revelators. Was quite intense. But I don't want to talk about this too much. I want to talk a little bit about how these things actually work. Now, so you have to imagine that in 2005, there was a lot of work had been going on. A lot of codes were developed. They had been used for 10 years, and they would be unstable. They would usually run maybe for 5, 6, 7 m of time evolution. So now we usually do thousands. The ring down period is it's about 17 m, and it was a little bit, and it would crash immediately. This problem for maybe like 10 years. So this was quite frustrating. People thought that they understood the issues of the problem, but it was just not working. And then this guy, Pretorius, he just tried a number of things which were completely different from everybody else, using the second order harmonic evolution and a number of other things. And so I guess also pretty surprisingly for him that just worked. Okay, yeah. Yeah. Mm. 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 Mm-hmm. No. Yeah. This was a real scientific revolution. Okay, you have to imagine there are people that this problem, and then you get an email. Say somebody claimed. Oh, it was really interesting to watch this. I mean, people were basically close to jumping out of the window. Okay, you have worked on this problem for 20 years, not solved. Well, no. Do with my life now. Okay. Yeah. There were essentially, but one of the most interesting things about this, basically two kind of people that dealt with this in two ways. One type was very frustrated because they've worked for this like holy grail problem. Now it's done. Is the end. What do I do now? Okay. And others say, oh, wow, now I can calculate all these new things that I couldn't do before. I can do a lot of science that before was not possible. All right. So I think it's easy to guess which side was more fruitful. Okay. The techniques that led to the breakthrough were not used anymore. Okay, there was just a few months later where it turns out, in fact, it works much better. Okay, and I'll talk a little bit about what's behind this, because there's some interesting geometry and some interesting understanding of black holes. What people had done before, in the mainstream, they had done something which in general is very, very smart. We've talked about, yesterday when we talked about initial data, we had this Einstein-Rosen bridges, right? This kind of things. I talked a bit about this yesterday. I talked about puncture initial data, and I talked about the fact that the quantity that you solve for, this conformal factor psi, this goes like something like 1 plus basically the mass over 2r, and so this is something which at r equals 0, this is singular. Okay? There's a way of factoring this out when we solve the elliptic equations for the constraints. But now when you want to evolve your metric, well, that's more difficult. So how should you do that? How should you evolve your metric? Well, there's something similar. There's something singular. I know what it is. So let's just factor this out from the evolution. Okay? For this, you have to do two things. First of all, this is in your, for example, your ADM equations, in your generalized harmonic equations. This is not one of your metric functions. Okay? So you want to write your evolution equations in a similar way than what you have done for the constraints. You say my 3 metric, for example, my 3 metric HAB, this is now psi to the 4 times some other metric h bar AB. So that you isolate this degree of freedom, which becomes singular. And then what you actually evolve numerically is essentially simply this minus this term. Okay? Every smart person will do that. I mean, how could you not, right? The problem is, now I have to check what I actually wrote on my slides. So one of the things that you have to do, if you want to factor this out, it's very inconvenient if your black holes move around, because then what you factor out, what is singular, so you choose coordinates to be a really good idea. Okay, you kind of know what the motion is, where they're not moving around. The problem, which I'll explain afterwards, is actually singularity in your data is not this one. It is there in the initial data, but in the evolution it changes completely. And so if you factor out something singular which isn't there, you put in an extra singularity in your evolution, and that's not a good idea. And that doesn't work. One of the reasons why Pretorius had this breakthrough, because he actually made excision to work. So he was excising a whole region where the singularity is, and he wasn't affected by that problem. If you don't use excision, which was very complicated and considered by many just too complicated for implementations, then this analytical method of factoring this thing out, it just didn't work. All right. So now, okay. So this is, we have seen this slide. If you went to the colloquium yesterday, I just want to remind you that there are so it's a big issue when you evolve black holes, that inside the horizon there is a singularity, and we have two ways of dealing with it. Basically excising it in space, just cutting a hole out of the computational domain. This is what Pretorius did. And then using singularity avoiding slices, where you choose a smart choice of time coordinate, so that your slice just stops short before the singularity, and the singularity is never reached. And you just deal with regular data, and you don't have an annoying hole in your computational domain. All right. Now, before we go to this, some interesting details, I want to present some kind of black hole gauge conditions wish list. So if you choose your coordinates for the evolution, what properties should they have? A very important one is that they should be symmetry seeking. What does this mean? Imagine you have your in-spiral of two black holes, all kinds of things happen. It's going to be actually your coordinate choice should be naturally attracted to an axisymmetric to coordinates in which your solution really doesn't depend on the angle. It's physically axisymmetric, but it doesn't mean that you have naturally property. And maybe even more importantly, if the final solution is time independent, the coordinates that you choose, your choice of time slice, should also make the solution look manifestly time independent. Okay? That may not actually be possible. Also, at least not the boundary conditions that you want to set for numerical relativity. Also, you want to keep your horizon fixed size, as also I mentioned yesterday. You don't want your horizon row at the speed of light. You want to stay. You want to have it stay nicely. This means what I've mentioned. Beta, this beta quantity in the 3+1 equations, you basically have to choose it outward pointing, and if you have a horizon, which is a null surface, 5 degrees, but who cares? So your vector, it moves up the horizon, and your grid points on the horizon are going to move with the speed. And so this movie here, this is actually from Pretorius' first talk, and you see the black holes doing all kinds of interesting things, and then they merge. And it looks very simple. What remains, so this is the lapse function. It's perfectly nice and symmetric, and it freezes into something time independent. So we can probably understand what the solution is, what it's doing. All right, we have seen this movie before. It's just a reminder. Looks very nice. Okay. We don't need this, I think. So now a few more comments. So we've seen so far the generalized harmonic formulations. This is just a shortcut of the slide which you have already seen. This is the heart of this formulation, how you write the Ricci tensor. But these are the evolution equations for the lapse and shift. And they look a bit complicated, but not too complicated. But what you can check for these equations is that, particularly if you have harmonic lapse, if the source terms are gone, then this is what we call marginally space-like slices. They will hit the space-time singularity, and the extrinsic curvature goes to infinity as time goes to infinity. All right? So this is kind of a mild way of approaching the singularity. It takes a long time, but it's not acceptable in a numerical evolution. So essentially, if you want to use this formulation, you have to use precision. You have to cut a hole in your domain, which is light, and you can use spectral methods and so on. So this approach is done in one of the very successful codes, the spec codes, and you want to combine harmonic with excision. All right. Now, if you think excision is too complicated for you because you can hire an army of postdocs and you don't have office space for all these people, then you want to use a different strategy. You want to use not excision, but use a smart choice of your coordinates, and you need an evolution system for the equations that goes with it. Okay, and so there's a number of choices, but the old standard is what is called BSSN or BSSN OK, with the initials of the authors. And now this looks very ugly equations, long, some completely ad hoc definitions here. Why do we do these definitions? Now there's some very we take the 80 equations, they're only weakly hyperbolic. And one of the key things to achieve this is you introduce a new variable, which is basically your Christoffel symbol contracted. You make this an independent that you evolve, and that, together with some other tricks of adding your constraints to the right-hand side, that makes your system hyperbolic. So it's well posted. But then I say that what you want to do is you want to factor out your conformal factor, write the metric in this way, and this is exactly what this thing is doing, except that the bar is now called a tilde, and the psi is changed to a the logarithm of something, so we write this as e to the minus 4 phi times the 3 metric. So this is just the same thing written a different way. So we have factored out this degree of freedom, and so now we can factor out this. Okay, so they make it better behaved for black holes. So then you use these new variables, and you rewrite your Einstein equations. You get something which looks slightly ugly, but it's not too bad. So this is what. So hyperbolic is also. I don't know why I wrote this. It's strongly hyperbolic. The symmetric hyperbolic is one space dimension. So this is what many people are actually using. Now you have to change. Now you have to choose your coordinates. Now coordinates. This is another problem which has taken people several decades to figure out. What should you do? The first thing is you've said we want our slice as t equals constant to avoid the singularity. This is called avoiding lapse. Okay, it's just a lapse function for this. And one of these functions has the right properties. And one of these gauges is called 1 plus log. And this is the equation. It's called 1 plus log because in Schwarzschild you can find an explicit solution. The explicit solution has something to do with writing there's 1 plus log of something. Okay? So what is this here? So there's the time derivative of the lapse. This is the Lie derivative with respect to the shift. So basically these two quantities together, these are the Lie derivative of the lapse in the direction normal to the slice. So this is the normal, this is the standard way of taking the derivative. And then on the side, so you can put a constant here, but this isn't really important. The important thing is there's a number, mostly chosen to be 2, and then the lapse, and then the curvature. Okay? If you write it like this and you study its properties, you will see that this is a lapse condition which just freezes the lapse in as you approach the singularity, which means a good deal before the singularity, but inside of the event horizon, this lapse is going to become 0 and it just halts your evolution. You just get stuck within the black hole. Right? So if you will draw this here, I think I make a little bit better Penrose diagram for these purposes. So here's let's try kind of 45 degrees. So somewhere here inside there's this kind of point where if you start with a slice here, it just can't go further, it just gets stuck because the lapse goes to 0. All right? Okay. Now, so that's solved, very nice. But now you have to choose some condition for your shift, which means you have to choose your spatial coordinates. How should we choose the spatial coordinates? The problem that people have worked for a long time, the kind of the train of thought to do this goes as follows. We have a lot of freedom to choose our coordinates. Let's choose our coordinates so that the metric looks kind of nice and simple. Okay? What does this mean? So for example, it means that the metric derivatives are small, or some metric derivatives are 0, which means that metric derivatives is the Christoffel symbol. So let's try to get as many components of the Christoffel symbols as 0 as possible. Okay? These kind of conditions, you can write them as an elliptic equation. An elliptic equation which tries to minimize a quantity, so for example, certain derivatives of the metric. All right? And then in principle, what you could do is you write your Einstein equations as some hyperbolic equations plus some elliptic conditions which give you nice and smooth coordinate representation of the geometry. The problem is that not only are these elliptic equations expensive, but you would have to have some boundary conditions at the horizon, which is complicated, which gives you all kinds of trouble. So instead, you have a really smart idea, which is the following. Let's say you want to solve an elliptic condition with some differential operator, some maybe linear differential operator, let's call it L, and you want the equation that L phi, let's say, is 0. And that's an elliptic equation. Okay? But you don't have to actually, to have coordinates, you don't have to have this elliptic equation satisfied exactly. You just want to be close to that equation. You want to be somehow attracted toward the solution of this equation. And so now what you can do now is you modify this to an equation like L phi is phi dot, or maybe phi double dot, depends on your taste. Like phi double dot, for example. Now this is it's a hyperbolic equation. Now it's a wave equation. This wave equation will have zero time derivative when the original equation is satisfied. And so what typically happens for a wave equation is the wave equation has excited. There's some initial profile. What does the initial profile do? It just disperses to infinity. Okay? So initially, you will not have good coordinates. That you solve this equation in time, the perturbations of, so the residual of this L phi is going to travel out to infinity under favorable conditions, and you will be left with an equation which satisfies this equation. Okay? And so approximately then you will have this satisfied. And so this is what is usually done in numerical relativity. In particular, there's a long line of history, but this particular evolution equation for the shift is motivated by one of these minimization conditions which try to minimize the distortions. Okay? Right, you can show that strongly hyperbolic, it's well posed, and you can be happy. There's I marked in color 2 free parameters, so you could change the 3/4 to something else. What that would change is this is the propagation speed of this elliptic equation, the characteristic speed at large distance, and 3/4 is set so that your propagation speed at infinity is 1, or the speed of light. That seems reasonable. And then kind of damping parameter, which I will explain. So there's this plot. I'll show the plot because I'm going to do. If you want to do black hole evolution in practice with BSSN formulation, you need to understand this parameter. Let's get rid of this. Let's see. So what would happen if your shift vector is just 0? Okay? You don't use this equation. You simply make your shift vector 0. In this case, your horizon is a null surface, so it expands out with the speed of light. Okay? So your horizon will just eat up the whole grid. Now, if I switch on my gamma driver shift, isn't going to do this, but my horizon is going to settle down very nicely to constant size. So my horizon maybe looks like that, and it settles down to some constant size. But now, if this term has a negative sign, it's opposed to the effect. So that means the effect of the whole shift is like slowed down. And so this initial expansion will take longer. And so therefore, my horizon is going to be larger. And so what this parameter simply does is it regulates the size of larger black holes in your grid. You make it the larger you want, smaller black holes make. All right. So if you want to, if you have to plan your how big your grids and boxes have to be, then this all goes together with the value for this parameter. If you look at the equation, you can check that this parameter is dimensionful. And so if you have a bigger black hole, you also have to scale this with mass. Okay, if you do the same simulation but for 2m mass instead of 1m, then you have to change the value. All right. We have said this basically already. Oops. So now let's talk about what happened to our numeric evolutions, continuing where we were before. So before 2005, where most people, what they did, they had these fixed puncture evolutions. So they did this, where we assume a particular singularity, and then we just factor this out, and it doesn't move across the grid, and that didn't work. So we assume that the geometric structure of our black hole is this kind of thing. All right. And so when people so in order to achieve this, people had set all kinds of quantities in the code of complicated functions. And so when they just deleted all of this, deleted the factoring out, deleted the changes in the code which makes the black hole move in space, then it just worked essentially out of the box very, very nicely. And so now the question is what's going on? And we'll see that the geometry is not at all this one, which we call it a trumpet. So how does this work? And this tells us a little bit more about the Schwarzschild geometry. So let's make a Penrose diagram of the Schwarzschild geometry once more. I'll make it a nice one. As nice as I can do. So here's our horizon. And maybe somewhere here, this is our initial slice. This is t equals 0, and t equals 0 has this geometry. So here we go at infinity. So from here, this point is a sphere. Maybe, it's this sphere, very large. And then we go here. The sphere is minimal. It's the minimal surface in the middle, and then we're somewhere here. The sphere it becomes again large. And so now we start our evolution. It goes forward, and so now we see that it settles down to a stationary solution. It is time independent, okay? So we watched this movie from before. Where is the movie? This one. This movie, we watch this and we see everything becomes time independent, okay? So obviously, when we evolve things, we have to look for a time independent solution, and we have to ask what are its properties. All right. So what do we do? So we can see our slice, our numerical solution. So it definitely enters the horizon, but we find an apparent horizon, but then we don't know what happens to it. Okay. Now we use a very interesting fact from mathematical relativity, which is that if the solution is stationary, and we have a horizon, it has to be a killing horizon. Okay? There's a killing vector, and there's a number of nice mathematical structure, and in particular, the killing vector here is going to be a null vector. Okay? So what we'll have here is that the metric, so GAB, so our killing vector is d by dt, because the symmetry is in the time direction, so we have a time-like killing vector. So we have this d by dt, well, maybe we should have done it this way. A d by dt b, and so here this is going to be 0. All right. So if I evaluate this quantity, I will see that at some point it's going to be 0. This is when it enters the horizon. All right. And then I'm going to evaluate this on the whole slice. And so if my geometry is this geometry, if this it comes out on the other side. And it has to become 0 once more, because it goes to the other side of the horizon. All right? And then I evaluate this, and there's 1 0 and the second 0. So I know my slice, it didn't get out on the other side. It's still inside. My t equals constant spatial slice, it's hiding somewhere in here. All right? Well, where did it hide? Where did it go? All right? And so in order to understand this, it's good to write down the Schwarzschild line element. Let's see if I can remember the line element. So the S squared is equal to minus 1 minus 2m over r. Oops. Let's get rid of this. Minus 1 to r dt squared plus the r squared divided by 1 minus 2m over r plus r squared, and then comes the angular line element, d theta squared plus sine squared theta d phi squared. So now what we're looking for geometry somewhere inside of the black hole. What's going on to this geometry inside of the black hole? You know that inside of the black hole, because of the signs that appear here, now r is a time coordinate and t is a spatial coordinate. Okay? And now we want to understand this geometry now. What is it doing? What is it doing inside of here? As we go closer to the singularity, so r, a time-like coordinate, now it approaches 0. We get closer and closer to the singularity. Now, so inside here we have constant time. So our time coordinate, which is now r, it's constant, so dr is 0. So we can forget about this one here. All right? Now what we see is that, so there's this parameter t, which is now a spatial parameter. So t is the parameter which goes along the slice inside. And we can see that nothing here depends on t. So there's a symmetry inside. What does this mean? This means that this inside r equals constant. So we can draw r equals constant. It looks like this inside. Outside r equals constant. Maybe it looks something like this. This is r equals constant. All right. So now, what is the geometry of that? The geometry of this is that of a cylinder, a three-dimensional cylinder. Okay, something as a spatial geometry, which looks like that. So these are my angular coordinates, and then in this direction is t, but nothing depends on t. So this has the same geometry here as there. It's a cylinder, which doesn't change. All these points here, all these points are geometrically the same. Okay, because I have used my 1 plus log slicing, I can compute what's the maximum cylinder, the closest which I can get to the singularity. And it's something like here. In fact, this has a value of Schwarzschild radius is 1.3 m or so, 1.31, whatever it is. So I can't go further than that. Oops. Well, in that case, I'll give you the tomorrow. Yeah. Let's go for lunch. Now we have a major scientific puzzle. What happens to the slice in Schwarzschild? We have all the equations. We can think about it until tomorrow. We can go for lunch. Oops. I'm very happy. If people give me feedback of what they absolutely have to hear tomorrow, I'm very receptive. Thanks.